In this video, I'm going to run through some of the situations with a converging lens and how you draw the ray diagram for each of those situations. This can be quite an abstract topic, and it's good if you can already have a general understanding of what this ray diagram is talking about. If you're looking at this now thinking, I've got no idea what this means, then you probably need to go away and look at that again first. I will, however, just briefly label this up. So you can see that in the middle I've got my convex or my converging lens, and then to either side at the same distance I've got my focal point, and I've also labelled on here twice the focal distance at both ends. And then this arrow here just represents my object, and obviously an object doesn't really look like an arrow, but that's just the way we represent it in a ray diagram. Now I'm going to draw 3 rays coming off the top of this object, and each one has a specific rule. So the first ray that you draw comes off the top of the object and it comes parallel to the axis. Now a ray which hits the lens parallel to the axis, the rule is that it then must go through the focal point on the other side, like that. The second ray that I draw goes through the center of the lens. And any ray that goes through the center of the lens, doesn't matter what angle it's at, it will always go through unaffected. And then the third and final ray that I will draw goes through the focal point on this side. And the rule is for this ray that any ray that goes through the focal point on this side, once it emerges from the lens, it will then be parallel to the axis. So it's sort of like a reverse of the rule for the first one. And so I draw that one on like that. And I want to get it so that these all meet. And then you can see that I haven't quite given myself enough space, but that's okay. So if I just extend my axis out a little bit over here, you can see that they all join up over here. I mean, it's not, it's not pretty, but you can see that that's where that happens. And then I can now draw an arrow like that. So what we do now is you compare the original object to the image of the object. And you can see here that the original object is pointing upwards, whereas now the image is pointing downwards. So we say that number 1, it is inverted. Secondly, the object was originally 1 line tall. The image is now more than 1 line tall. So we say it is magnified. And finally, if I was to put a piece of paper here, then that image would project onto that piece of paper. So where the rays converge, if I put a piece of paper here, I will see the image on that piece of paper because these rays do actually converge here. So it is a real image. And that happens, you get this result whenever the object is placed between the focal length and twice the focal length of the lens. So every lens is a different focal length, and the object, if it's placed between the focal length and twice the focal length, you will get this result here. Okay, so let's move on to the second scenario. Okay, again, if at any point you're not sure about something or you want to recap it, just pause it and go back, and you can make a note of something or you can just listen again. But now we're going to do when the object is placed more than twice the focal length away. So we follow the same rule again. So I have my first line comes horizontally off, and then that will go through the focal point on the other side. Then my second ray goes through the center of the lens, and any ray that goes through the center of the lens, doesn't matter what angle it's at, it remains unaffected, so that just goes straight through. And then my final one, hopefully, is going to end up over here, but we'll see. We'll follow the rules and see what happens. So the third ray goes through the focal point on this side, and then when it gets to the lens, it becomes parallel. And you can see that it does line up quite nicely there. So now I can draw on my arrow for my object, and we can make the same analysis that we did for the first example. The arrow of my original object points up from the axis, this points down from the axis, so this image is inverted. Here it is 1 line tall, here is less than 1 line tall, so we say it is diminished or smaller. And again, if I was to put a piece of paper here or a screen, it would project onto that screen and I would be able to see the image, so it is a real image. And you will get those results anytime you place the object greater than twice the focal length of the lens. So it might be useful for us to think about when this might be when we might come across this kind of magnification. So this is easy to imagine. Okay, we take an object and we get a bigger image, so anything like a projector is going to be doing that. All right, we shine a light behind an object, it goes through the lens, and we end up with an image projected onto a wall, which is much bigger than the original image. Okay, and if you've seen old camera film or video film, you'll know that the video film, the image on that is very, very small, but by passing it through the lens, we'll be able to create a very big image. Conversely, a camera or your eye will do the opposite. In order to get a real image onto a small piece of camera film or onto the retina at the back of your eye, then we need to use this kind of situation, because it will take a large object and create a small real image. All right, so a camera and a projector are sort of the opposite of each other. So the camera takes a large object and produces a small real image that can be put onto film, and then the projector takes the small image on a film and can be used to make a large projected image. All right, and also what this means is that these objects continually need to be inverted. So anytime you look at an image if you go to the movies, then, you know, or perhaps in the old days it would be like this. I'm not sure how the cameras work these days, but the image would need to be upside down, or the object that you're projecting would be upside down, so that this would end up the right way up. Okay, so there's one more situation, and that is when the object is closer than the focal length. Well, something a little strange is going to happen here, but we just go with the same process that we did for the other two situations. So we start by drawing our first ray, which is horizontal to the axes. Now, remember, of course, that these aren't the only rays, the rays coming off in every direction, but by drawing these specific rays, it allows us to understand what is happening. And the horizontal ray will go through the focal point, as usual. And then we draw the second ray, and the second ray goes through the center and is unaffected. And immediately we can see that this isn't looking good, because these rays are not converging. Even though it's a converging lens, they don't appear to be going into one point like they did up here. So here they came to this point, here they came to this point, whereas now that doesn't appear to be happening. And then, of course, if we want to draw a ray through the focal point, it's going in the opposite direction. Okay, so in this case, we're not going to even bother drawing that line, because it's not it's not a line, it's not a ray that's going to go through the lens. So we just ignore it. Okay, So we said in both of these previous situations that the image is always formed where the rays converge. Here and here. So what you do here is we can now extrapolate these lines back. Remember, extrapolate just means to carry on beyond a certain point. So if I extrapolate them back like that, and I extrapolate this one back in a similar way, try and be as accurate as possible. All right, what you see is they do converge, and they converge over here. So this now is my image, okay? So I'm going to label this up. So I've got, this is my actual object, but this here, this is my image. Now, these rays that I've drawn in dotted lines, these aren't real rays. Remember, the actual rays of light are coming off the object and going through the lens. Just like with the mirror, these are the rays from where it appears the object is coming. Okay, so if you imagine if you're down here and you're looking through the magnifying glass, these rays appear to be coming from an object up here. And we can still do the same analysis that we did before. All right, now you'll see that my object is pointing up from the axis, my image is also pointing up from the axis, so it is upright, it is not inverted. Secondly, we can see that the image is bigger, so it is magnified. However, these rays are not actual rays of light, so we say that it is a virtual image. And what that means as well is that if I was to place a piece of paper here, I wouldn't be able to see the image projected onto the piece of paper. And that makes sense because this is obviously how a magnifying glass works. Okay, so you know, Sherlock Holmes, he has his magnifying glass. If you've got one at home, you can get it out and use it. So you have to look through the magnifying glass. Up here, all right, so in a projector, the image is projected onto a screen and you just look at the screen. Whereas here, you must be looking through the lens. Okay, so you look through the lens and then here's the object, but you see the object as being bigger than it actually is. Now, if you were to hold the magnifying glass, remember this is the magnifying glass here, if you were to hold the magnifying glass in your hand, and then this is the object you're looking at, and if you put a piece of paper behind the object that you were looking at, and then looked at the piece of paper, you wouldn't see any image on that piece of paper. All right, now there's demonstrations we'll do in the classroom which will show how that works more clearly. So those are the three situations I'm going to go through today. Number one, where it's between the focal length and twice the focal length. Number two, where it's beyond the twice the focal length. And number three, where it's inside the focal length. It's also useful thinking about other situations. The other two obvious situations are, what if it's at exactly the focal length? What do I get then? And what if it's at exactly twice the focal length? What do I get then? And also what I will say is, you could memorize if it's between the focal length and twice the focal length, then I get an inverted magnified real object. If it's more than twice the focal length, I get an inverted smaller real object. And if it's less than the focal length, I get an upright magnified virtual object. But that's going to be very difficult for you to do. It is much, in this case, in this scenario, it's going to be much more effective for you to be able to follow the rules of how to draw a ray diagram, and then interpret the results of the ray diagram.